What is going on, guys? Welcome back. In today's video, we're going to do a crash course on the Python package called NetworkX, which is the package for graph theory for working with graphs and visualizing graphs or networks in Python. So let us get right into it. Alright, so NetworkX is a quite comprehensive Python library, which means it has a lot of different functions, it has a lot of different functionalities. There are a lot of things that we can do with NetworkX, but in this video today, in this crash course, I want to focus on the fundamentals, so using NetworkX to do some basic graph theory, some basic network analysis, to create graphs, to visualize graphs, to represent graphs in different ways, to generate different types of graphs and stuff like that, to calculate certain metrics. This is what we're going to focus on in today's video. And for this video, I'm going to assume that you at least know some basic graph theory, so you understand what a graph is, you know what the difference is between an undirected graph and a directed graph, what the degree of a node is, what nodes and edges are in the first place, stuff like that. I'm going to explain some of the functions and some of the concepts as we go, as we talk about the different features of NetworkX, but I'm not going to explain graph theory from scratch here. Here and there, I might introduce some basic concept or explain some basic concept, but I expect you to understand the basics of graph theory. So we're going to focus more on the implementation, on the application of NetworkX in graph theory rather than on graph theory itself. So in order to use NetworkX, we need to first install it. We're going to open up the command line and we're going to say pip install NetworkX. And once we have that installed, we can go into our script and import NetworkX as NX. This is the commonly used alias. Now you don't have to use it, but it's what everyone does. So if you use NetworkX, it's the same as saying import NumPy as NP, import pandas as PD. You say import NetworkX as NX. We're also going to import here matplotlib.pyplot as PLT. So if you don't have matplotlib installed, you can also install that using pip install matplotlib. This is only used to show the visualizations that we create using NetworkX. And we're going to start here now by creating simple graphs, like empty graphs, just a basic graph object without any nodes and edges. And for this, we have different constructors. So the most basic one is to say nx.graph. And nx.graph is just a simple undirected graph. So the edges go in both ways. We don't have directions. It's just a simple undirected graph. Now, if we want to have a directed graph, we say nx.digraph, so digraph, directed graph. This then means that when an edge goes from A to B, it doesn't necessarily also go from B to A because the edge has a certain direction, namely from A to B. Then we also have nx.multigraph, which basically means a graph where we have multiple edges between nodes, so we can have double edges and stuff like that. And we also have the directed version of that, which is the DI multigraph, or actually the multi-DI graph, sorry. So a multigraph, which is also directed, because this one is undirected. Those are the basic four graph types that we can use here, that we have constructors for. And when we create such a graph, let's go with an undirected one, we can add edges sequentially. So I can just say here g.add_edge, and I can add a new edge from 1 to 2, for example. So you can see the first parameter is u and the second one is v, meaning one node, second node. And the good thing about NetworkX is that it automatically recognizes, since there is an edge from 1 to 2, I don't need to define that there are nodes 1 and 2. By creating the edge, I also create the nodes. So if 1 doesn't exist, if 2 doesn't exist, it's going to create those nodes because implicitly we're defining them by saying that there is an edge between 1 and 2. We say that there is a node 1 and there is a node 2. We can also provide a weight, so we can say, okay, now there's also an edge from 2 to 3. We can say that the weight of this edge, so the importance or the speed maybe, which is not the same as the PyQt5 weight, so let's remove that. The weight of this edge is going to be 0.9, and whatever you do with that weight is up to you. You can say, okay, the weight means speed, so the higher the weight, the better, or it means how strong the connection is, or you can also interpret it as a cost function. So for example, saying that the higher the weight, the more difficult it is to get from 2 to 3, or the longer it takes, something like that. We can also do that with letters, and the cool thing is we can actually pass everything that's hashable. So we can say G add an edge from the string A to the string B, for example. This works. We can also create an edge from B to B. We can also just add individual nodes. So we can say G add node C without connecting it to anything. And whatever we want to pass, we can pass. We can pass anything that is an object in Python. So I can go ahead and also say I want to add a node, which is just a node print, referring to the print function. We're not calling it. We're passing the print function, the object, the entity of the print function. We're passing it here as a node. This also works, and we can then go ahead and visualize this graph that we now have by saying G, or actually, sorry, not by saying G, by saying nx.draw, and we have different types of visualizations. We're going to talk about those here in a second. Let's just go with draw spring. We're going to draw the graph G, and we're going to draw it with labels. So with underscore labels, so that we see the names of the nodes, and then plt show. And when I run this now, you can see that this is our graph. This is our graph being visualized. We have A connected to B, B connected to itself, 1 to 2 to 3, C standing on its own, and the print function also as a node being its own graph, subgraph, you could say, or component. So that's the basic idea. We create graphs, we add edges, we visualize them. That's the most basic thing we can do. Now, instead of adding the edges like this, we can also directly create a graph from the edges, or we can add from an edge list. So we can say, for example, we have an edge list, and this is just a list of tuples, and these tuples represent edges. So we can say 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, 3 is also connected to 5, and then maybe 4 is connected to 6, and 6 is connected to 7. So that's a basic edge list, and we can use that list to create a graph, either by saying nx from edge list. That is one way to do that. So we can just pass the edge list here, and we can run this, and then we have the graph. Or we can just delete this and say nx graph, and then we can say g.add from add edges from, and we can pass here the edge list. So that also works. Now, what else can we do? We can represent these graphs in different ways. So this is the edge list representation, but we can also have an adjacency matrix. So an adjacency matrix basically just means we have a matrix where we have the individual nodes listed as columns and as rows, and when in a directed graph, basically, when you have the value 1 for a column and a row, it means that the node, which is the column, has a connection to the node, which is the row. So if I have the column B and K, it means that B is connected to K if there is a 1 in that particular field. If I have K and B, it means K is connected to B. And if it's undirected, it's always the same. So we always have both being set to 1. That's the basic idea. We can also just get this representation easily by saying here G equals, or actually not G equals, sorry, print, and then I can say nx.adjacency matrix of G. So I create this graph from the edge list, and then I have here the adjacency matrix. This is just representing the individual indices. And what we can also do here is we can also create an adjacency matrix using NumPy, which is another package that you would have to install. So import NumPy snp. So pip install NumPy if you don't have it. What we can do here is we can create an adjacency matrix ourselves, and then we can use that to create a graph. So instead of adding from the edge list here, let's comment that out. We can go ahead and say, for example, np.array. And I want to have a list of lists. I want to have 0, 1, 0, and then 1, 1, 1, and then 0, 0, 0. What that basically means is that this only makes sense for a directed graph, but this basically means that if this is ABC, ABC, it would mean that that B is connected to A, B is connected to itself, A is connected to B, and C is connected to B, but B is not connected to C. That's what that would mean. But as I said, I'm not going to explain these basic concepts here in too much detail. And we can just say now nx dot from numpy array, and then like this. I hope that's enough. No, this does not seem to be enough. What did I make wrong here? I created the array from numpy array. Let me just see where the problem is. Okay, I need to fix that here. Okay, that's a pretty obvious and stupid mistake. We are creating an empty graph after creating this one, so it doesn't display this one but the empty one. So let's just run this again. And now you can see that this created this graph. So we have 1 being connected to itself. 1 is the second one because we have a 0 as well. So we can see here the diagonal, 1 being connected to itself. Then we have 0 being connected to 1, 1 being connected to 0. And I think since this is not this is not a directed graph, so it doesn't actually matter the directions. But this is how you can create a graph from an adjacency matrix. So you can take a graph, turn it into an adjacency matrix. You can also take an adjacency matrix and turn it into a graph object. And now let's look at the different visualizations. Now, basically, it's always the same. We just plot individual nodes connected by edges, but we can do that in a different, we can arrange the nodes differently. So let's just go ahead and create this graph again. What we can do here is we can use Spring, or we can use a bunch of other styles, you could say, or algorithms to determine the position of the node. So we can do draw Spring to do the one that we already know, but we can also go ahead, for example, and say draw circular. So circular like this. And then you're going to be able to see a difference. This is Spring, this is circular. It tries to arrange the nodes in a circular way. We can also do shell, which tries to do concentric circles. Then we have, then we can go with spectral, which uses Laplacian, what was it? Laplacian, I don't know what exactly it was, something with eigenvectors. I'm not exactly sure what the theory behind this is, but they're just different representations. And we can also just use random here, so we can plot the graph randomly with labels always set to true, obviously. So as the name says, this is going to be just completely random. And then we can also, this one is quite interesting, we can also draw a planar graph. I hope this is how it's pronounced. I have to Google this here in a second before I use the term too often and I mispronounce it. But basically this means that it's going to plot it in a way that the edges don't intersect. So if possible, obviously. So those are the different things. Those are the different functions. We can run them now and you can see the difference. This is Spring. This is circular. This is shell, which is basically concentric circles. So it's quite similar. This is spectral. This is random. And this is, I hope it's pronounced planar. Meaning that if possible, we don't want edges to cross each other. So if we can draw it so that no edge crosses another edge, that's what we want to do here. Let me just Google how it's pronounced.
Planar.
Planar. Okay, wasn't that wrong. So when we draw a planar graph, that basically means that, as I said, we don't want the edges to cross each other, but that's not always possible. So we can look at an example here. So I can choose to display the graph K4, which is a complete graph, meaning that we have 4 nodes and all the nodes are connected to all the other nodes. So I can go ahead and define it myself. I can say 1 is connected to 2, 1 is connected to 3, 1 is connected to 4, 2 is connected to 3, 2 is connected to 4, and 3 is connected to 4. That would be the K4 graph, the complete graph. And we could display it as spring and as a planar graph. And in this case, the spring representation crosses the edges. You can see this edge crosses this edge. They intersect. Here, it is not the case because it's possible. For the K5, for example, it's not possible. If we have 5 nodes and all the 5 nodes are interconnected, it is not possible to do a planar representation. And I'm going to show you what happens if we try to do that. It's going to give us an exception. But before we do that, I want to show you that we don't have to manually generate a complete graph. So I don't have to define the edges of the complete graph manually. I can just go ahead and say here G equals complete graph, or actually NX complete graph, and then 4. That basically results in the same thing. And I can also do now the same thing for 5, and you're going to see what the problem is. It plots it like that if it's the spring function, but when I try to do it planar, it says G is not planar, so it doesn't work. Yeah, that's basically the idea of that, because the K5 is known to not be a planar graph. Yeah, that's basically it. Now let's look at how we can get some information about a graph that we have. So for example, here we have the complete graph. How can I get the degrees of the individual nodes? In this case, the degree of all the nodes is going to be the same because they're all interconnected. But maybe to make this more interesting, let's return to the graph that we had before, this one. We can get some information about that by just going ahead and saying print dictionary. We're going to turn into a dictionary, the g.degree, and we can just get the individual indices here. So for example, I can go index 2, and I'm going to get the degree of, I'm going to get the degree 3. Which one is that? I think that is, which one has a degree of 3? Let me just see it here. Oh, this is a K4. This is actually not what I wanted to do because they all have degree 3. Do I have something? What was the graph that I had before? Where is it? There you go. We can do the same thing here now. Let me just remove all of this. And then let's go ahead and say print dictionary g.degree and then index 2, for example. This is going to give me 2 as a result, and I think that is this the node 2? I think it's node 2 because we have, no, we don't have a 0 actually, do we? No, it's a dictionary, not an index, so it's actually a key. That was a mistake. We're not asking for index 2, we're asking for key 2, which is the node 2, and this node has a degree of 2. This one would have a degree of 3, so if we go and say degree of 3, this is going to give us 3 in the command line here in the output. So we can get the degree of the individual nodes quite easily. We can do the same thing with the in degree and the out degree by saying in underscore degree and out underscore degree. At least I think that's the case, even though PyCharm says it doesn't know that function. But this only makes sense in a directed graph. So maybe we can see that that is the case so that you don't have to believe me. If we have a directed graph, now we have the directions, which means that the in degree of 3, for example, is 1 because we have 1 incoming connection, and the out degree is 2. So let's go ahead and see what the in underscore degree of 3 is, what the out underscore degree of 3 is, and also what the degree in general of 3 is. Let's see. And we get 1, 2, 3 because the in degree, as I said, 1 incoming, 2 outcoming, total of 3 because that plus that is that. That's quite simple. Okay. So what else can we do? We can also find shortest paths. Let's look at the graph. I can find, now this one is a directed graph. Let's go back to an undirected graph so that it's simpler. Let's say I want to find the shortest path. Now the problem here is that we only have, let's add an additional path, 2 being connected to 8, 8 being connected to 9, 9 being connected to 4. So 2 to 8, 8 to 9, 9 to 4. I think that should accomplish what I'm trying to show you here. Can you please display this in a planar way? There you go. So now to get from, what was it, from 2, in order to get from 2 to 4, I have 2 paths. I can go 2, 3, 4, or I can go 2, 8, 9, 4. And I can find shortest paths quite easily by just going ahead and saying print nx dot shortest path in the graph G from 2 to 4. And then I will get 2, 3, 4. This is the shortest path. If I remove the node 3, or if I remove the edge from 2 to 3, it's going to tell me that 2, 8, 9, 4 is the shortest path. So if I remove this edge here, you're going to see that the path is now 2, 8, 9, 4, obviously. Okay, so that's quite simple. We can find shortest paths. What we can also do is we can get information about the centrality of individual nodes. And I don't want to come up with some fancy examples here because that would require too much thinking now and it would be boring. But essentially, we have different types of centralities. We can have the degree centrality, the closeness centrality, the eigenvector centrality, the betweenness centrality. Basic idea being that we want to know how central is a node, how well positioned, how centrally positioned is a node in the graph. And we can decide that in different ways. So we can say, for example, that the degree of a node is the most important indication. How many nodes this node is connected to is the most important thing in terms of centrality. So we can say that the higher the degree of a node, the higher the centrality of the node, the higher the degree centrality of the node. We can also say the closeness centrality, which is a different thing. This is the average distance to all the other nodes. So we calculate the shortest path to all the other nodes. What's the average distance to get to all the other nodes from a certain node? So for example, let me just open Paint maybe for an example. I hope I don't come up with the stupid one here in my improvised drawings. But let's say I have a node like this one here, and let's say it has only one connection, but it has a connection to this node here, and this node is connected to basically all the other nodes. Something like that. Let's say we have a million nodes here. And then let's say that I have one bridge here somewhere, and then I have a node that is connected to 2 other nodes. Now this node has a degree of 3 because it has 3 connections. And let's say here again we have millions of nodes, right? And maybe let's say we have some more nodes in between so that we have some more distance. This node would be more central than this node, even though it has less connections in terms of closeness centrality, because it's way faster in reaching all these other nodes. Because it's just closer to a very central point here, even though this one has a higher degree because it is connected to some very unimportant nodes. That's the basic idea of the closeness centrality. The eigenvector centrality also takes into consideration the importance of the nodes it is connected to. So it cares about how connected it is to other nodes, but it also cares about the quality of the other nodes. Because if you're connected to a lot of unimportant nodes, you're still not so important. But if you're connected to very important nodes, even if there are fewer, you're more important. And then we have also the betweenness centrality, meaning that betweenness meaning how much percent of the shortest paths in the graph run through you. So if we have all the shortest paths, how many of those important paths, of those optimal paths, run through you? Because that is the betweenness centrality. How often do people have to cross you to get to or to use their shortest path? Now that's a lot of theory again, but essentially what you want to do is you want to say nx dot and then degree centrality and then G. For example, print whatever, and then you get this dictionary here. So that is the dictionary showing you the degree centrality of all the nodes, and you can do that now for all the different centralities that we discussed. So for the closeness centrality that we discussed, for the eigenvector centrality, and for the betweenness centrality, and I think there will also be other centralities that I didn't cover here. But you can see the values here in dictionaries. And I think I have here a good example. I'm not sure what exactly I wanted to show with that, but I'm sure I'm going to figure out as I'm explaining here. But we have a graph 1, which is a complete graph. So we have a K5 graph. So G1 being a complete graph 5, and then we have G2, also a complete graph 5. And then let's say I have, I want to relabel the nodes of G2. Because the basic idea is I want to have now two very interconnected graphs, and then I want to have a bridge. I want to connect them via just one connection. I want to connect, for example, I have 0, 1, 2, 3, 4, and I have A, B, C, D, E, and I want to connect 4 to a node X and X to a node A, so that X is basically the bridge combining these two complete graphs. So it's going to be very important in terms of between the centrality, but not so much in terms of degree centrality. So if I say G2 equals nx.relabel nodes, let's relabel them here with the following dictionary. 0 is going to become A, 1 is going to become B, 2 is going to become C, 3 is going to become D, and then 4 is going to become E. Then what we're going to do is we're going to say that G is going to be, or actually let's create the graph first. G connector is just going to be a simple graph, nx from edge list. And here we're going to provide now the following edge list. The node 4 is going to be connected to a new node X, and this new node X is going to be connected also to A, making it the bridge for our graph. And we're going to say that the total graph G is nx compose all. So you can use that function compose all to connect graphs. And we're going to say that it's just the combination of G1, G2, and G connector. And then we can get rid of all this here. Now, planar is not going to be possible, so let's just go with spring. And then you're going to see now that our node X is here in the middle. You can see that all the other nodes basically have a higher degree of centrality, or a higher degree centrality, I should say, because they have a degree of 5, or at least, no, 4. Most of them have a degree of 4. A and 4 have a degree of 5 because they're also connected to X. But this node is super important in terms of in-between centrality, in between the centrality. So what I can do here is I can say now print, and I can say nx.degree centrality of the graph and nx betweenness centrality of the graph. And then we're going to see, hopefully, that the degree centrality of X is super low, 0.2. It's the lowest of all the nodes, but you can see it's the highest of all the nodes in terms of betweenness centrality. Because even though this point here is not well connected to all the other nodes, it is super important and it's super central because it is at the center of the connection. That's the idea here. So this is something that you can do as well quite easily. You can also get some basic metrics about the graph, like you can say print nx density of graph G, or the diameter. And basically the density means how many edges do we have divided by the total number of possible edges. So we have certain nodes, and the graph where all these nodes are completely interconnected, the complete graph version of these nodes has the maximum number of possible edges, the maximum number of edges possible. How many of those, how much percent of those do we actually have in our graph? So in a complete graph, this is going to be 100%. In a not complete graph, it's going to be something less than 100% because it's not going to use all the edges. That's the density. The diameter is basically just the longest, shortest path. So if we have all the shortest paths between the nodes, what's the longest one? That's the diameter of the graph. So in this case, we have 0.4 just because of X, because X is not connected to all the nodes possible. So we don't have all the possible connections. 40% of the graph is connected. So we have density of 0.4, and the diameter is 4 because the longest, shortest path is 4. Which one is that? Basically 0, 4, X, A, for example. Or no, actually 0 to 4, 4 to X, X to A to B, for example. And I think that most paths here have a length of 4. All right, so what else can we do? We can find certain paths. So I'm not sure if it exists in this particular graph, but you can find a, I need to Google what that is called again, how that is pronounced. How to pronounce Euler, let's see.
Euler.
Euler, okay. Actually, I pronounced it correctly. So if you want to find an Euler path or an Eulerian path, I hope that's how it's pronounced, basically you can just go and say nx dot this path here, and you can pass the graph, and it's going to give you that path if it exists. Now, what is this path? It's essentially going through each edge exactly once. Now, let's see. We need to turn this into a list. It's not always possible to find it, because in some graphs it's not possible to have such a path. In this case, it would be possible. Now, let's print this before we visualize so that we can actually track it. The basic idea is that you want to go through you want to visit each edge exactly once. And how you do that is, in this case, one possible way, if not the only way, is, I mean, I don't think it's the only way, is it? I guess not, because you can do the same thing starting at A, but you can go 4 to 0, 0 to 1, 1 to 2, and so on. You go through all these edges, you follow this path, you can pause the video and try to do that, and you will not go through an edge more than once. Now, you can visit nodes multiple times, but you will not use the same edge more than once, and you will use each edge at least one time, or exactly one time in this case. That's the idea of this path. You can also find groups, basically complete maximal subgraphs, by just saying nx dot find cliques. What's the pronunciation here? Graph theory makes it easy to pronounce things when you're not a native speaker. You notice how little you know. But essentially, this is the maximal subgraph that we have here. And in this case, we have 4x, ax, this complete graph here, and this complete graph here. So those are the 4 complete subgraphs that we have. Complete meaning, again, all the nodes are interconnected. And since this is a K5 and this is a K5, obviously we then have this one here, or those 2 here, because 4 and x, when you have 2 nodes that are connected, obviously they're going to be a complete graph. And since we don't have anything else with x, this is also the maximum complete graph. And we can also do nx.k underscore core to find, what was the definition of this one? Subset of nodes where all nodes connected to at least, where all nodes are connected to at least k other nodes in the subset. That's something that we can do here as well if we want to. So there are a lot of things. I don't want to cover all the functions. What I want to do, though, is I want to show you also how to find bridges, and bridges are defined as edges that, when deleted, increase the number of complete connected components. So when you have a graph that is fully connected and you remove something, one node, and the removal of this node, or actually edge, not node, the removal of this edge causes the graph to not be connected anymore. So you have 2 connected graphs now, 2 connected components. That edge is a bridge. So what we can do here is we can say print nx.bridges g, and this should give us, okay, we need to call the list function on it. This will give us 4x and ax. Obviously, these 2 connections are bridges, because if you get rid of them, you're separating the 2 graphs here into 2 separate connected components. So that is a bridge. Now, a local bridge is essentially when you have edges between 2 nodes, and those 2 nodes don't have any common neighbors. So it's not actually a bridge, because you're not, when you delete that edge, you're not actually separating the graph into 2 connected components, but you remove an edge that connects 2 points that are not somehow connected by similar neighbors as well. So you're basically removing the connection between those 2 points, and they now have to go a longer path to find each other. So that's a local bridge, and the span of this local bridge is essentially what the distance of the shortest path is after removing that edge. And you can find these local bridges by saying nx local bridges of g, and you can see in this case we don't have local bridges because those are complete graphs, but we do have a bridge, and a bridge is also a local bridge with the span being infinite, right? But for example, if I now have also A being connected to, let's actually do that. Let's say I have A being connected to a node what's the last letter? We used E. A being connected to F, F being connected to G, G being connected to H, and H being connected to 4. Now this is no longer a bridge, but it's a local bridge, because if we remove it, we have to go along our path. So I can actually go ahead now and say, let's add here as well. What was it? 4 being connected to F. And 4 is not a string, so let's change that. 4 being connected to F, F being connected to G, G being connected to H, and then H being connected to A. So now it's no longer a bridge, but we have a local bridge. So you can see we don't have a single bridge. The list is empty, but we can see here that when we remove 4 and X, this is a bridge of length 5, or span 5, because if we now remove it, I have to go through this path here to reach 4. So it's a local bridge. But it's not a complete bridge, because I still have a path to reach the other side of the graph if you want, if this edge here is removed, or this edge here is removed. Yeah, so that's that. Okay, so what else can we do? We can also list the connected components, and that's actually the last thing I want to show you here, because I don't want to bombard you with all the different concepts. You can explore the library on your own, but I want to show you here how we can find connected components. So let's say we're going to get rid of all this here. Let's say that these two graphs are not actually, let's just go ahead and leave it like that. When I now go ahead and say print G or NX dot connected components, that basically means, I need to list this, basically means that they're connected, right? So in this case, the whole graph is a connected component. Now let's remove the edge from X to A. Now we have different connected components, because now we have the components 0, 1, 2, 3, 4, X here. This is one connected component. And DEACB here, this is also a connected component. So, and of course, if I remove this edge here, we're going to have 3 connected components. That's the basic idea. Now, in directed graphs, it's a little bit differently. I'm not going to do it here now in Python, but what we can do is we can do weakly connected components and strongly connected components. And the basic idea here being, when we have a graph, let's say this point is pointing to this point, is pointing to this point, or actually, let's do it the other way around. Let's say they're pointing here, and let's say those are pointing to each other. Now, they would be connected because I can reach B from A and I can reach A from B, but I cannot go from C to B or from C to A. So it would not be, this whole thing here would not be a strongly connected component. However, it is a weakly connected component, because if we ignore the directions of the edges, it would be a connected component. So that's the basic idea here. And we can also find these components with those two functions. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.